Let us see the torque acting on a dipole in uniform electric field. So let's suppose there is some uniform electric field in this region. Okay. So how is uniform electric field represented? It is represented by equidistant parallel lines. Okay. Because if lines get closer, that means the electric field is strong in that region. If lines are separated, means the electric field is weak. Okay. So electric field is uniform means the electric field lines are equally separated from each other, okay, and they are parallel to each other. So this is uniform electric field. Okay, uniform means it's in same direction and it has got same magnitude everywhere. Okay, electric field intensity is equal. So we keep a dipole in this electric field. So let's suppose the dipole is kept like this. Okay, so this is charge minus q, this is charge plus q, this is charge plus q, this is charge minus q. Okay, and there is some angle between this electric field E bar and the dipole moment. So dipole moment is directed from minus q to plus q, right? We learned yesterday that electric dipole moment, it is directed from minus q to plus q, right? So suppose a dipole is kept in this uniform electric field and P bar, which is equal to q into 2a multiplied by p cap, is the electric dipole moment, is directed at an angle of angle theta with the electric field. Okay, so this much angle is theta, right? The angle between dipole and the electric field is theta. So now what happens? So why there is a torque acting on this dipole? So there would be a force acting on positive and negative charges due to this electric field, right? So force on positive charge will be directed like this. Okay, it will be pushed by the electric field, and force on negative charge is directed like this, right? So these are equal and opposite forces because the charges are equal in magnitude. The force due to electric field acting on them is equal. Okay, so there is a force on positive charge as well as negative charge. Force on positive charge is directed like this. Let's call it F plus bar, and force on negative charge is directed like this. Let's call it F minus bar. Okay, so what is F plus bar? It is force on positive charge, force on plus Q due to the electric field due to E bar. And similarly, F minus bar is force on minus Q due to the electric field. Okay, so the forces are equal and opposite. Okay, so magnitude of these two forces. So F plus bar, the magnitude of F plus bar is equal to magnitude of F minus bar, and it's suppose it is equal to F. So what is this F? F is equal to what? Charge multiplied by electric field, right? So F is equal to what? Magnitude of the charge multiplied by magnitude of electric field. Okay, because electric field is force acting per unit charge. Okay, electric field. So if we consider this as a test charge, then electric field would be what? Force acting per unit charge, F upon Q. So F is equal to what? Q multiplied by E, right? Clear till this point? Okay. Then see, now we have two equal and opposite forces. Okay. two equal and opposite forces acting on this dipole. So we know that equal and opposite forces, if they act on some body, they rotate that body, they exert a torque. Okay, so a system of two equal and opposite forces is known as a couple. Okay, and couple rotates a body, it creates purely rotational motion, right? So now how much would be torque due to this couple? So I can say F plus bar and F minus bar, they form couple. So therefore torque on dipole due to this couple would be equal to what? So we know the magnitude of torque is equal to magnitude of one of the force multiplied by perpendicular distance between two forces. Okay, so I can say it is perpendicular distance between forces multiplied by magnitude of one of the force. Magnitude of one of the force. Right. Remember this? Yes, no. Okay, this is torque due to a dipole. Sorry, this is torque due to a couple. Okay, so we know magnitude of the force, it is Q multiplied by E. We have to find out perpendicular distance between these two forces. Okay, so see, this distance is 2A. So if I stretch this line, okay, if I stretch this line, uh, let us use this thing only. And draw a perpendicular from here. Okay, this is not visible. Sorry. So I'm stretching this line and drawing perpendicular from here. So this much is perpendicular distance between two forces. Okay, this force F plus bar acts along this line, F minus bar acts along this line. So this much is the distance between those two forces. Okay, so this angle is theta. This distance is 2A. So we can name it, let's call it AB is the dipole and this point is C. So this distance BC is the perpendicular distance between the two forces, right? And in this triangle ABC, we have sine theta equals to BC divided by AB, right? So I can say in triangle ABC, sine theta equals to BC divided by AB. Okay. And therefore, what is BC? BC is equal to AB multiplied by sine theta. So BC is equal to AB, which is length of the dipole, multiplied by sine theta, right? So the perpendicular distance is AB sine theta. Okay, we can substitute that here. So this is equal to AB sine theta multiplied by magnitude of one of the force, which is Q multiplied by E. And what is AB? It is 2 times A. Okay, it is 2 times A. So we have Q multiplied by 2 times A. So I can write it like this, Q into 2A multiplied by E into sine theta. And what is Q into 2A? It is magnitude of electric dipole moment, right? So this was P into E into sine theta. P multiplied by E multiplied by sine theta. This is the torque acting on dipole in uniform electric field. So this is the magnitude of torque, and we know torque is a vector quantity. What will be its direction? All right. So torque is equal to P multiplied by E multiplied by sine theta, P sine theta. What will be its direction? So see, to find out direction, we have to represent the torque in terms of vector product of P and E. Okay. So it can be P bar cross E bar or E bar cross P bar. Right. It can be P bar cross E bar or it can be E bar cross P bar. Which of these two will be correct? Let's check. Okay. So see, uh, this is this force F bar. Okay, it is pulling the dipole towards right. Okay, this one is pulling the dipole towards left. So in what direction will it be rotated? Clockwise or anti-clockwise? It will rotate clockwise, right? This one is pulling it towards right. The other one is pulling it towards left. So if you pull it towards right and this force is acting towards left, it will rotate clockwise. Okay, this is mirrored image, so you might see it anti-clockwise. Okay, so now see, if you take, so this is direction of P bar, this is the direction of E bar. If you take E cross P, so using the right hand thumb rule, okay, if you take E cross P, you want to find out resultant. So you start from first vector, that means you have to keep your right hand in direction of first vector, then curl your fingers towards the second vector. So are your fingers curling in clockwise direction or anti-clockwise direction? It is anti-clockwise. So it cannot be E cross P, right? It would be P cross E. Okay. So if you take this as a first vector, okay, P bar is directed from minus Q to plus Q. Electric dipole moment is directed from minus Q to plus Q. And E bar is like this. So if you take this one as first vector, this one as a second vector. So then you keep your right hand in direction of first vector, curl your fingers towards the second vector. Okay. And stretch your thumb. So stretch thumb will give you direction of torque. Okay. But rotation will be given by your curled fingers. Okay. So now your fingers are moving in clockwise direction. Okay. And that's what these two forces are doing. They are rotating the body in clockwise direction. Okay, so that means which one of these two is correct? E bar cross P bar or P bar cross E bar? P bar cross E bar is correct. Okay, so in vector form, I can say in vector form, the torque is equal to P bar cross E bar, not E bar cross P bar. Got it? Yes, no? Whatever we studied since yesterday, let us solve some questions based upon that. Okay, so let's see let's see first question. 3-point charges plus q, minus 2q and plus q are placed at points. So these are the points. X is equal to 0, y is equal to a, z is equal to 0. Then x equal to 0, y equals to 0, z equals to 0. And x equal to a, y equal to 0, z equal to 0 respectively. The magnitude and direction of the electric dipole moment vector of this charge assembly are. Okay, so we want to find out the resultant dipole moment of these charges. So first charge is at x equal to 0, y equal to 0, z equal to 0. Second one is at, sorry, y is equal to a. Okay, this one is at x equal to 0, y equal to 0, z equal to 0. So this one is at origin, and x equal to a, y equal to 0, z equal to 0. So z coordinate for all three is 0. That means the charges are kept in xy plane only, right? Since z coordinate is 0. Okay, so let us draw these charges. So x is equal to 0, y is equal to a. So you keep that first charge. So let's suppose this much distance is a. Okay, and you keep charge plus q here. Then second charge is minus 2q. So it is at origin. So minus 2q is here at origin. And x equal to a, y equal to 0, z equal to 0. So x is equal to plus a. So there you keep another charge plus q. Okay. So now there will be some dipole moment from negative charge to positive charge. So you take one of these two negative charges. Okay, you take minus q. So there will be a dipole moment from minus q to plus q, and a dipole moment from another minus q to this plus q. Okay, and dipole moments will be directed like this. So this will be, let's call it p bar. This one is p bar. Okay, so now how much would be the net dipole moment? So net dipole moment is vector sum of these two. So it will be directed like this because the magnitude of both of these is equal. It will be directed like this. So resultant would be in this direction. Okay. 45 degrees. Okay. So this is resultant. And how much would be resultant? So it will be just, so let's suppose this is P dash. Okay. This is P and this is P. So we can keep it here also. So this is P dash. Okay. P dash bar. This is P bar and this is P bar. Okay. So using Pythagoras theorem, we can say that P dash square is equal to P square plus P square, right? Then it is 2P square. So therefore P dash is equal to square root of that. Okay, so it is equal to 2 times, sorry, square root of 2 times P. Okay, and what is P? So P is equal to Q multiplied by distance between the charges. So distance between charges here is A. Okay, so this much distance is A, right? So it is, this is equal to square root of 2 multiplied by Q into A. Okay, so we have habit of writing this distance as 2A, but here the distance is equal to what? A. Got it? All right. So this is the magnitude, and what will be the direction? So let's check. It is directed along x equal to 0, y equal to 0, z equal to 0, and x equal to a, y equal to a, z equal to 0. Okay. So actually this one would be answer. Okay. Why? Because see, this point is at x equal to 0, y equal to a. So this much distance is a. This much distance is also a. So this dipole moment would be directed in this direction, right? Along this line. So what are coordinates of this point? So if we think about xy plane only, x coordinate is a and y coordinate is also a. So it is a and z coordinate is anyway 0, right? So this is a 0. So in what direction it is directed? From 0 0 0 to a 0. Okay, got it? Yes, no. Let us see next problem. A point Q lies on the perpendicular bisector of an sorry a point Q lies on the perpendicular bisector of an electrical dipole of dipole moment P. If the distance of Q from dipole is R, much larger than size of the dipole, then electric field at Q is proportional to. So tell me, this is very simple. It lies on perpendicular bisector. So this is your dipole minus Q plus Q, and point lies on the perpendicular bisector. That means it is on equator. Okay. So this is point P. This is some point. Okay. Let's see. So the electric field at this point, it is proportional to. What is the electric field at equator? So E equator is 1 upon 4 pi epsilon naught multiplied by P upon R cube or X cube, you can say. So it is directly proportional to P, inversely proportional to R cube. So it is option D. Okay, let's see next question. I guess there would be some network issue or something. Don't know. An electric dipole is placed at an angle of 30 degree with an electric field intensity 2 multiplied by 10 raised to 5 Newton per coulomb. It experiences a torque equal to 4 Newton meter. The charge on the dipole, if dipole length is 2 centimeter, is. This is very simple question, right? Because we are given that there is dipole kept at an angle 30 degree with electric field. So this is electric field and it experiences torque. So everything is given. Okay. So we know tau is equal to PE multiplied by sine theta. Okay. And we want to find out charge on the dipole. So it is okay. So charge is suppose Q. So P is equal to what? Q multiplied by 2A into E sine theta, and we want Q, so we'll take all other things on other side. So it is tau divided by 2A multiplied by E sine theta. Okay, right? So torque is given. Torque is 4 Newton meters. Okay, so 4 divided by length is given. It's 2 centimeters. Okay, it's not A, it is 2A. Okay, so 2 multiplied by 10 raised to minus 2 multiplied by electric field is 2 into 10 raised to 5 and sine 30 is half. Okay, so this 2 and 2 gets cancelled. 10 raised to 5 multiplied by 10 raised to minus 2 is 10 raised to 3. Take it in numerator, it's 10 raised to minus 3. So 4 upon 2 is 2. So the answer is 2 multiplied by 10 raised to minus 3 coulombs. So that is 2 millicoulombs. Okay, option B. Next question. A dipole of dipole moment P bar is placed in uniform electric field E bar, then the torque acting on it is given by. Okay, so dipole is kept in uniform electric field. What is the answer of this question? It is option B. Right, this is just formula. Okay, so we have to remember this formula. Okay, we have to remember all the formula actually. Next question. What is the angle between the electric dipole moment and electric field strength due to it on equatorial line? Tell me. Option A, 0 degrees. It is 180 degrees. Okay, so electric field at equatorial point. Okay, electric field at equatorial point is directed opposite to the dipole. This is minus q plus q. Okay, so dipole moment is directed like this, and the electric field is directed opposite to that. Okay, this is electric field. So how much is angle between them? It's 180 degrees. Okay, yes, no. Tamil Selvi, what's the formula? E equatorial is equal to 1 upon 4 pi epsilon naught multiplied by minus p bar divided by r cube, or if we call this distance x, then x cube. So how much is angle between them? It is 180 degrees because we have this negative sign in formula. Okay, this is simple, right? Next question. An electric dipole of dipole moment p bar is placed in uniform external electric field E bar. Then option A, torque experienced by dipole is E bar cross P bar. Okay, this is not true. It is P bar cross E bar. Torque is 0 if P bar is perpendicular to E. So is this true? Torque is equal to PE sine of theta. Okay, angle between them is 90. Then torque is maximum actually. Okay, so if this angle is 90, then sine of 90 is 1. So torque is maximum. Okay, so this is not true. Option C, torque is maximum if P bar is perpendicular to E bar. This is true. Okay, so this is the answer. Then potential energy. So we didn't learn about potential energy. We'll learn about it in next chapter. Okay, all right. So we don't need it here. Answer is option C. Torque is maximum if P bar is perpendicular to E bar. Right? The electric field at a point due to an electric dipole on an axis inclined at an angle theta to the dipole axis is perpendicular to dipole axis if theta is. Okay, so this is the question. So electric field is perpendicular to dipole axis if theta is. So see, this is suppose our dipole, and this is the point where we want to find out the electric field. Okay, this is minus q, this is plus q, and this is the dipole moment. Okay, direction of dipole moment. This angle is theta, this angle is theta. Okay, so we want to find out electric field at this point, right? So what we had done is we had resolved this dipole along two perpendicular axes. Okay, so one along this one. So what was the component? So we can draw it like this. Okay, so this is P cos theta. Okay, and for this component, the electric field, sorry, for this component, this point is, it lies on the axis. Okay, so there will be some electric field due to this component, this dipole moment, and then the other component we have is directed like this. Sorry, directed like this. Okay, so this one would be P sine theta. For this component, the electric field at this point is, sorry, for this component, this point is equatorial. Okay, so we can say that there would be some electric field due to this component at this point. What will be its direction? it is directed like this only. So this dipole moment is directed like this. Okay, for axial point, we know the electric field is in same direction as that of the dipole moment. Okay, so the electric field due to this component is directed like this. So let's call it E parallel. We called it E parallel. Okay. And then what about this component? So for uh, the equatorial point, the direction of electric field is opposite. Okay, it is opposite to that of the dipole. So this one would be E perpendicular. This one would be E perpendicular. So net electric field is vector sum of these two. Okay, net electric field is vector sum of these two. So it will be directed something like this. So question is, the angle between this dipole and the net electric field is 90 degrees. So suppose this angle is something, okay, this is theta, suppose this is beta or something, okay. So this angle, because see, if this is perpendicular to this, that means this angle plus this angle is how much? 90 degrees. Okay. So theta plus beta is equal to 90 degrees. Right? Got it till this point? Yes, no? Okay. So then we have to find out this beta. Okay. No, we have to find out theta only. All right. So see, what would be E perpendicular? What is formula of E perpendicular? It is 1 upon 4 pi epsilon naught. Let's call it K only, multiplied by P upon R cube. Okay, this is the formula. But it is caused by this component. It is not P, right? This dipole moment is not P, it is P sine theta. It's P sine theta divided by R cube. Okay, and what is E parallel? Is electric field due to this component of the dipole. So it is K multiplied by 2 times the dipole moment upon R cube. Okay, for axial point, the electric field is K constant, that is 1 upon 4 pi epsilon naught multiplied by 2p upon R cube. Okay, but it's not P, this is P cos theta, right? Now see, you want to find out this angle beta. So what would be tan of beta? So this is, okay, if you put it here, so this becomes opposite side. Okay, this is the adjacent side. Okay, if I put this E perpendicular here, okay, this is E perpendicular. So tan of beta is equal to E perpendicular divided by E parallel, sorry, E parallel. Okay, so if I divide this by this, what do I get? So K P R cube will be cancelled. It is sine theta divided by 2 cos theta. Okay, so it is sine theta divided by 2 times cos theta. So that means it is half of, okay, so tan beta is equal to half of tan of theta. Okay, this is what we get. Half of tan of beta. Sorry, tan of theta. Okay, and what about, all right, so we know this relation that theta plus beta is equal to 90 degrees. Okay, can we relate tan of theta and tan of beta? Okay, These two are complementary angles, right? So for complementary angles, we know tan of one angle is equal to cot of the other. Okay, sum of two angles is 90 degrees. Then tan of one angle is equal to cot of other angle. Okay, so tan of beta is equal to, I can say, cot of theta. So I can substitute cot of theta here. Cot of theta is equal to half of tan of theta. That means I can move this on this side. Sorry, this is not cos, it's cot. Okay. So this is 1 upon tan theta. You can move it on other side. So you get tan square theta equals to 2. That means tan of theta equals to root 2. Okay. And therefore theta equals to tan inverse of root 2. This is the answer. Tan inverse of root 2. It's option C. See, most of the questions are simple. Okay, most of the questions based upon the electric dipole are simple. There are some questions like this which are little bit tricky. Okay, but once in a while. And it is not from NEET. Actually, in NEET, there were not, there were 3-4 questions only. So first 4 questions that we discussed, they were from NEET, and all other questions, I thought 4 questions is very less, right? So all other questions are from some different exams. Okay, but that doesn't mean there cannot be a question. Okay, these are uh, actually 3-4 topics. So let's see next question. The electric field due to an electric dipole at a distance r from its center in axial position is E. Okay, so E axis is equal to E. If dipole is rotated through an angle 90 degree about its perpendicular axis, then the electric field at same point will be. So this is very, very simple. Right. Dipole is like this. This is your dipole. Okay. Minus Q plus Q. And the electric field at an axial point at this point. Okay. The electric field due to this dipole is E. So right now this is an axial point. Now if dipole is rotated through 90 degrees, so if you rotate this through 90 degrees, what will happen? About its perpendicular axis. Okay, about a perpendicular axis. So the axis is perpendicular to plane of this paper, you can say. Okay, so the dipole, new position of dipole will be like this, right? So this is plus Q minus Q, or okay, this will be minus Q and this will be plus Q, depending upon how you rotate it. So it's rotated by 90 degrees. Okay, so this point will be at equator now. So how much would be the electric field there? It will be half of the earlier electric field, right? Because E equator is equal to half of E axis. Okay, now the point has become equatorial point. So it is half of E, right? Option C. So this one was extremely simple. Next question. Charges situated charges situated at a certain distance along the axis of electric dipole experience a force F. Experiences a force F. Okay. So when charge is on the axis, it experiences force due to dipole. It is F. the distance of charge from dipole is doubled, then the force acting on it will become. Tell me. Okay. See, this is dipole, okay, and keep some charge on the axis. Okay. So this is charge, some, okay, let's call it delta q or something. Okay. So this is minus q, this is plus q. So now there will be some electric field due to this dipole at this point, right? So electric field is E axial. Okay. So electric field due to dipole at this point is E axis. How much would be the charge? How much would be the force acting on delta Q? It is the charge multiplied by electric field. Okay. So it is E axis multiplied by delta Q, which is equal to 1 upon 4 pi epsilon naught multiplied by 2p upon r cube multiplied by delta Q, right? Now what you are doing is you take this charge, move it at twice the distance. Okay. So what will happen? So distance is doubled, force becomes F dash suppose. So force is inversely proportional to R cube, right? Force is some constant, this constant upon R cube, because charge will remain same, dipole moment is same, everything else is same. So it is inversely proportional to R cube. Okay. So you can say F is equal to K upon R cube. So F dash will be equal to what? K divided by 2R cube, because distance has become 2R now. So that is K upon 8R cube. Okay. And what is K upon R cube? It's F. So this is equal to F upon 8. Option D. So this is very simple question. Next one, the electric field and the potential. Okay. So sorry for taking this question. But anyways, the electric field and potential of an electric dipole vary with distance r as. Okay. So potential, sorry, the electric field due to dipole is inversely proportional to r cube and the potential is inversely proportional to r square. We'll learn it in next chapter. Okay. So the answer of this question is 1 upon r cube and 1 upon r square. It's option D. We'll learn this, that potential of electric dipole is inversely proportional to r square. Okay. We'll learn this in next chapter, right? Let's see next question. An electric dipole placed in, okay, an electric dipole placed in a non-uniform electric field experiences. Option A, both a torque and a net force. Option B, only a force but no torque. Option C, only a torque but no net force. Option D, no torque and no net force. What is the answer? We discussed this, right? It's option A, both torque and net force. There will be net force also and there will be some torque also. Now let us discuss a small topic. So let us discuss continuous charge distribution. Okay. So what is continuous charge distribution? So we learned various methods of charging bodies. Okay. So for an example, let's suppose we have a linear body like this. this can be a glass rod. Okay, suppose this is a glass rod from the first experiment that we discussed, charging by rubbing. Okay, so now when you rub this glass rod on silk cloth, some charge will be developed on this glass rod. Okay, so now this glass rod loses electrons, and that's why it becomes positively charged. So now this charge can be uniform, it may not be uniform. Okay, so what I mean is charge can be distributed. Charge can be distributed like this, or it may be distributed like this, that there is a more charge here, there is some charge over here. Okay, there is no charge in between, there is some charge here, some charge here. Okay, or it might be distributed like this. Okay, so in first case the charge is equally distributed everywhere. Okay, and in second case there is some charge here, there is no charge in between, there is some charge here. Okay, so charge is present in bits and pieces. So now this case is known as continuous charge distribution. What do you mean by continuous? It means that there is a charge at each and every point of that conductor. Okay, there is charge everywhere at each and every point. Okay, so if it is so that there is no gap between two charges on this point, on this body, then we say that the charge is uniformly distributed. Okay, it's continuously distributed. So if it is the case, then we can define a quantity like this. So this is a linear body. We can define the linear charge density. Okay, lambda equals to charge on body divided by length of the body. Okay, lambda is charge on body divided by length of the body. So now see, Q is total charge and L is total length of this body. So now if I consider some small section of this body, some small portion of the body, let's suppose from here to here, I consider small portion of this body, this much portion. Okay, so let's call the length of this portion, I'm sorry, length of this portion is suppose dl. Then we can say that charge on this portion is suppose dq. Okay, so charge on the portion is dq, length of this portion is dl. Then we can find out lambda by using dq and dl, as lambda equals to dq divided by dl. Okay, so it doesn't matter how much length we take, the charge on that length, I'm sorry, so it doesn't matter how much length we consider, the charge on that length divided by the length would be same everywhere. Okay, so if we consider complete rod and take charge upon length, we will get some value, we call it lambda. Now we take half of the rod, so charge will become half. Okay, if we take 1/4 rod, then the charge on that much length would be 1/4. Okay, so whatever length we consider, the charge on that length divided by the length itself would be, will give us same value. Okay, and what does that mean? That now what we can do is we can find out charge on any length. So we can find out dq. So if we find lambda, which is q upon L, we can find out now dq, charge on this much length. We don't know, suppose. Then dq will be just equal to what? Lambda multiplied by dl. Why? Because we know that if we take ratio of charge and length anywhere, it will be equal to this lambda. Okay. So knowing the length, we can find out the charge. Is it clear? And this we can do charges uniformly distributed only. All right. So this is called continuous charge distribution. Okay. So then we can take another example of a linear body like this. So for an example, we can consider a ring. Sorry. We can consider a ring. So this is also a linear body, right? So for a ring also, we can define the linear charge density. Okay. So if there is some charge distributed on this ring, Q is the charge. We can find out the linear charge density for the ring, and it will be equal to Q divided by its length. So what will be its length? 2 pi r. Okay. And then if you want to find out the charge in any length, so let's suppose from here to here, so what we can do, we can find out charge on it. So suppose the charge is dq. Dq will be equal to what? Lambda multiplied by dl. Okay, got it? So similarly, now this was linear body. These were linear bodies. So instead of linear bodies, we can have planar bodies. Okay. What do you mean by planar bodies? A sheet. Okay. Magnet is also continuous charge distribution. Actually, in magnets there are currents. Okay, so it is moving charges. Charges are moving in magnets. We'll learn about that. Okay. So it's not continuous charge distribution. Charges are rotating inside the magnets. Okay. All right. So these were examples of linear bodies. So instead of linear bodies, we can have planar bodies. So like we can have a square or a rectangular sheet. Okay. And we can imagine uniform charge distribution on this square sheet. Okay. So now see here the quantity of relevance is area. Okay. So now we have to define quantity called surface charge density. Okay. Surface charge density we denote by letter sigma. Sigma is equal to charge, total charge divided by surface area. So Q is the total charge and A is the surface area. Surface area of this rectangle. Okay. So then if I want to find out the charge on any small section. Okay, so if I consider any small section like this. Okay. So suppose area of this small section. This section has area equals to dA. Then how much would be the charge on the small section? So the charge will be suppose dq. So dq is charge on area dA. So we can say dq is equal to what? Sigma multiplied by dA. Okay, so charge is equal to what? Sigma multiplied by surface area if the charge is uniformly distributed. Okay, continuous charge distribution is there. So it is sigma multiplied by dA. Okay, fine. This is simple. And similarly, uh, similarly we can have uh, solid objects. Okay, for an example, a sphere or a cube. So we can have a cube or a sphere, and the charge can be distributed in the complete volume of these objects. Okay. So here charge is distributed uniformly, continuous charge distribution is there in the complete volume of this thing, of this cube. Okay. So here charge is distributed, charges continuously and uniformly distributed, sorry, uniformly distributed in the volume of this cube. Okay. So here we have to define a quantity known as volume charge density. Okay, so since the charge is uniformly distributed all over the volume, we define volume charge density, and we denote it by rho. So rho is density, mass upon volume, right? So just like that, here we define charge upon volume. Okay. So here rho means charge divided by volume. Okay. So rho is total charge divided by total volume. So now, if we want to find out charge in any volume, we can imagine small volume here. Okay. We can take a small cube like this, whose volume is dV. Okay. dV is the volume of this cube. Okay. So then dq is suppose charge on dV. dq is suppose charge on dV. So we can find out dq. dq will be just equal to what? The surface charge density, sorry, volume charge density multiplied by the volume. Okay, volume of this section. So it is rho multiplied by dV, right? So continuous charge distribution is kind of a simplification using which we can find out charge if we have linear bodies, we can find out charge on any length. If we have planar bodies, we can find out charge on any small area of that body. And if we have solid bodies like this, okay, a cube or a sphere, and the charge is uniformly distributed all over the volume of those bodies, then we can find out charge in any small volume, okay, like this, using the concept of continuous charge distribution, considering that charge is uniformly distributed everywhere on the body.